be correlated with birth and death rate. So I show here a few examples. So on the microevolution side of things, stuff like body size, environment, mating system have been proposed. And then more on the epidemiological side of things, so stuff like host location, host behavior, antibiotic resistance. So these are just examples, right? So there are a lot of these traits. And the fact that there are a lot of them is what led us to go more on the hypothesis, free kind of models that Jeremy Boyer was talking about previously. Because we didn't want to have to test all of these traits separately, one at a time, and also there is also some issues with coding the traits when you're doing your trait-dependent analysis. So we're kind of going for a model that is hypothesis-free, and so roughly the model is depicted here. So we have a number of observed states, each state being correlated to a specific birth and death rate. So one particularity and a difference with, for instance, BAM that has been discussed earlier, is that we assume that there is an underlying true number of states. So we're not speaking states just out of the distribution. We're not sampling the rates like from a continuous distribution. We assume there is this underlying number of regimes, and we're just sampling them on the tree. And so we infer, however, the number of states. So this isn't a parameter that is fixed in the model, it's inferred. And then so we have then state changes along the tree that occur at a certain rate gamma, and then each of these changes are going to lead to a new state at random. And so since we have a fixed number of states, that means that the same state can also reoccur multiple times. And so as I said, each state up to n is associated with a birth rate and a death rate. And then, of course, you have sampling events at the end of the tree. So this is the model we're using to calculate then the likelihood. And it's currently implemented as a these2 package. So that's also a feature that allows us to make inference either from a fixed phylogeny as other methods, but also use that as a tree prior if you want to do full inference from a sequence alignment. So using the these2 machinery basically for the inference of the tree. As I said, this is the hypothesis-free model, so there is no data on the states at the tips or at the root or anywhere else, basically. And one of the main assumptions we make when we calculate the likelihood is that there are no state changes in the extinct parts of the tree. So in the parts that we don't observe, the state doesn't change. This is quite a strong assumption, and I am actually going to show some testing of that assumption and its effects on the result later in the presentation. But yeah, so we have a bunch of datasets that we have been using to test the method. So we have simulated datasets, so birth-death process simulated forward with 1, 2, or 5 states in the true model. Full extent sampling, but no extinct sampling. So our simulated datasets so far are exclusively ultrametric trees. And so we simulated datasets both with and without changes in the extinct parts of the tree. So we are testing both versions, and we run the analysis just with the fixed true tree since we're trying to test our model and not the tree. The tree inference has not been modified in our implementation. And then we have an empirical dataset that is, so this is phylogeny that was previously analyzed using BAM, so it's also there run with a fixed tree simply because we want to be able to compare the results with what BAM got, and BAM is using fixed trees, at least in the current implementation of things. So these are results with the rates estimate, so on the left side relative error and on the right side the coverage. We have in red the gamma, so the rate of state changes in the tree. We have in green lambda, so the birth rate, and in blue mu, which is the death rate for each state. And these are averaged across the whole tree, so they're not per state. So we can see that overall on the birth rate, sampling in those simulated data sets, and extinction rate is quite famously difficult to estimate on these. So yeah, that's probably one element. The rate of state change is a bit harder to estimate, but you can see there are strong differences. In certain data sets it's really bad, and then in some data sets it's really good. So these two, this is the data set with only one state. So here the rate of state change to truth is 0, but we never reach that number in the MCMC. So this is why the coverage is just pretty awful, but then we are really close. It's just 0 is never included in the confidence interval. And these two data sets where the coverage is also pretty bad are data sets where the true gamma is high, so there are a lot of state changes on these trays. And so in these data sets, gamma is underestimated because some of these state changes will lead to states that will only be on the tree for a short amount of time. So there will only be maybe part of an edge or maybe one or two edges. And so these are really hard to estimate, so we may not be able to find them, especially if they happen closer to the tip. So this is the explanation. But overall, we have pretty accurate parameter estimates, especially so the buffer and the depth rates are reliable on all of the data sets, so we can accurately estimate those. And so we've looked also as to how the state positions are inferred. So do we have a good estimate of which steps are in which state compared to, well, what the truth is. So this is the clustering distance, so the lower the better. And this is the estimated number of states. So here the blue is the estimated, whereas the green and red are truth. So we can see that we overestimate the number of states most of the time. So the number of states is not, except when there are a lot of states, in which case we underestimate the number of states. So the number of states that is estimated by our model doesn't seem to be a very reliable metric. So that's one downside of this model. Since we don't fix that parameter, we're not actually able to recover it very well. But on the other hand, we are able to place steps in states reliably. We have more difficulty, again, when gamma is high, because there are a lot of changes closer to the tips. So a lot of tips that are in truth are misidentified basically during the inference. Overall, we have reasonably accurate, I would say, distance, however, on the clustering between the truth and the inference. Well, I'll keep talking and then eventually maybe the figure will show up. I don't know. So I wanted to show the empirical data set. So the original analysis by BAM was showing two different patterns. The first one was a pattern of time dependency where there is a so the figure is only partially showing up, unfortunately. I don't know what happened there, but anyway, so this is supposed to be the tree that we inferred with our method, and so the different color indicates the birth rate here. So from dark red, which is lower, and up to green, which is higher birth rate. And as I said, so there is an original analysis by them. I showed two things. The first one, the time dependency, where edges that are closer to the root had higher speciation rates on average than edges that are closer to the tips. And it also showed two clades, two families inside that tree that had a higher rate overall. Now we recover the time dependency, so this will be shown by the figure for sure. But we do see the same pattern in our results. However, we do not see the clays with higher diversification rates. All of the clays seem to have the same, basically the same diversification regime and the same values overall. So here we have a little bit of a discrepancy. There is a lot of possible explanations for that. The model that our method are using is different from that. We also use different priors on our settings. So there are a lot of possible explanations here. Now, as I said, we also did an evaluation of the approximation. We approximate that there are no state changes in the extinct parts of the tree, as this is an approximation that has been criticized because it's obviously not true in real data sets, and so its impact on the results remains to be evaluated. So we did an implementation without this assumption, so using an existing implementation in another package. So the first conclusion is that there is definitely a performance impact using the full likelihood requires numerical integration, and so that leads to things that are 6 to 10 times slower. On simulated data sets, we have better estimates of gamma with the full likelihood, so which means that we are closer to the true rate because we are able to estimate the rate as well in the unobserved parts of the tree, so that's kind of expected. We do slightly worse on death rates. It's difficult to see if this is an actually true pattern, or this is just small variations in the MCMC because the values are really close. On empirical data sets, another thing that's interesting is that the full likelihood is less sensitive to the prior on gamma, so less sensitive to the prior on the rate of state changes. Again, the figures don't want to show, but I have a figure with the lizard's phylogeny again, so our empirical data set that is showing the full likelihood versus the approximate likelihood. Overall, the trays are really similar, so you're not missing out on much because it doesn't want to show. Yeah, the values are slightly different. So the higher regime is a little bit higher in the full likelihood, so we have higher estimated rates close to the roots and lower to the tips. But overall, yeah, values are really similar. Anyway, so this is unfortunately frozen and I'm running out of time, so I'm just going to go through the conclusions. So we are able to estimate using this model the rates, as I said, of birth and death, and we are able to estimate their positions in the phylogeny. Time dependency can be recovered. We have shown that the approximation only affects our results slightly, at least in the data sets that we have tested, and its performance impact, as I said, is really big. And yeah, future work, hopefully we can work on reducing the dependency on the prior gamma. Yeah. And if you like the talk, there are other methods that are working on a very similar lineage-specific birth and death rates. You might want to check these out as well to see if they match closer with your data set, or if you don't like something that I've just shown there. Anyway, these are acknowledgement my co-authors from Basel, the